Good afternoon. Good afternoon, everyone. Welcome to this special edition of the NITEX colloquium. We have a public lecture this evening as part of the celebration of the inauguration of NITEX. Our speaker is Dr. Matthias Troja. Matthias has a very impressive CV. He's at the moment a technical fellow and corporate vice president at Microsoft, in charge of all things quantum. Several moons ago, he did his PhD at the ETH in Zurich, yeah, and then spent some time as a postdoc at the University of Tokyo, and then came back to Zurich as a professor of computational physics and joined Microsoft in 2017. Since a few months, he's also an honorary professor at Stellenbosch University in the School of Data Science and Computational Thinking, which is quite appropriate. So we are very happy to have it in our Stellenbosch family. Yeah. He also received several prestigious prizes that maybe I don't read now because you can all read, I assume. Yeah. So Matthias, we are very, very happy that you came the long way to Stellenbosch for today, and that you even volunteered to give us a nice, promising talk on a quantum future of computing. So we are all looking very much forward to your talk. Thank you very much.
Thank you. It just thought back that it was kind of 30 years ago that I first came to South Africa, and on the first day when we landed, and the friend of ours who I think is listening in now took me to a party at the university. So my first night in Africa ever was actually here. But I want to talk today about what drives me for the last decade or more, namely always how can we do more in science with computing? How can we do more in computational science? And that led me to the point where I said, for the problem I want to solve, I want to have, I need to have the quantum computer. And that's why I then joined Microsoft to help build one. What is the ultimate reason for that? Let's see how I can. Oh, I seem stuck here. Okay, so the reason is that over the last 4,500 years, we have not changed the way we compute. The fastest GPU works on the same principles as the abacus. That is changing with quantum computing. It's the first time in millennia that we change the way we compute. We don't just make them faster, we compute differently. Because scientific discoveries always lead to new technologies. It started with thermodynamics, led to the steam engine and the Industrial Revolution. Maxwell's equations, electromagnetism led to telecommunications and ultimately the computer. 100 years ago marks the start of the quantum age, and we are now seeing how that impacts communication, sensing, and computing. So I want to talk a bit about how it is different and what it can do. The quantum age started with the realization that particles are not always particles, particles can be waves. The light is the wave, but then Einstein in 1905 realized it sometimes acts like a particle. And then in the same way, the particles can be waves. The electron, the orbitals and wave functions are the sign of that. The idea of quantum computing is to use that for computing. It's a simple model for quantum bit of the fundamental processing unit of the quantum computer would be just like a classical bit. Let's take two boxes, two quantum dots, there might be, and let's put an electron into the right box. That could be the value 1 for a classical bit. Or we put into the left box, that's the value 0. But then we heard electrons cannot just be particles, they can also be waves. So what if this electron is in a wave state with some amplitude being 0, some being 1? That's the basis of a quantum bit. Now we're working with both values at once. We're working with this wave nature with the amplitudes in the two states. But as long as we don't look at it, anytime you look at an electron, you know where it is. You might have heard of Schrödinger's cat. You take such a quantum bit and you couple it to a poison machine that kills the cat if it's 1. But now that cube is in the state got the 0 and 1. So the cat is dead and alive in this same wave nature. But have you ever seen a cat running around that's both dead and alive? The answer is no, because whenever you look at a qubit, it's 0 or 1. Whenever you look at an electron, you see where it is. When you look at the cat, you see whether the cat is alive or dead. So when you look at this wave nature that's hidden here, you look at it, you open the curtain, you measure it, then it turns out to be 0 or 1. In this case, 0, the cat is alive. So that will be important when we then think through how we use quantum computing. Because here you can see when this quantum bit is in this wave state, then some amplitude is 0, some is 1. So it can be in two states at once. So when I compute on this, I compute in both the states 0 and 1. What if you go further? If I have two quantum bits, there can now be 4 states, 4 values, 0, 0, 0, 1, 1, 0, 1, 1. I go to 3 quantum bits, and I have 8 states, 0, 0, 0 to 1, 1, 1. If you want to simulate that on a classical computer, then 3 qubits means I have to go through 8 values, and I need to store the amplitudes for these 8 values. If I go to 20 qubits, then I have a million different states and need 60 megabytes, and I might need my cell phone to simulate it. If I have 30 qubits, it's 2 to the 30, about 1 billion states. To store all the amplitudes, need 16 gigabytes, and need a fast laptop. If we go to 50 qubits, it's 2 to the 50. The 10 to the 15 states that need 16 petabytes of memory. That's the biggest, fastest super computer on the planet. Just imagine adding another 10, going to 60, 70, 80. But when you reach 250 qubits, then this wave describing the state of all the configurations of the qubits has more values than the atoms in the visible universe. That means you will never build a classical computer large enough to store that state of the quantum system. So because you need exponential memory to store the state, there's a potential for it to do lots. But the next question is not just, hey, that's a great machine that I can simulate. I want to turn it around. I want to use this quantum computer to do things that I just could not do classically ever, to advance computational science, to solve problems. And for that, I want to learn how I compute with quantum, meaning how we use these wave patterns, how we manipulate the waves to do a good calculation. And so let me show you the way we compute classically. I have some function x that I want to compute for many different values and want to find, for example, the maximum of the function. So classically, what I have to do for that, I have to go through it, do the calculation one number after the other until I find the largest one. Quantumly, with the qubits, what I can do is I can prepare the argument register in all possible values at once. I just prepare a wave that has all the values. Then I compute the function and have the results for all the input values. So and that's why people say a quantum computer is so powerful, because it can compute in exponentially many ways at once. It can explore all possible options simultaneously. Okay, it's a great starting point, but it's a bit naive, because remember, I told you when you look at the Schrödinger cat, it's either dead or alive. And so where this idea of the quantum computer being so powerful because it can compute in all the values at once breaks down is when I actually want to read out the value. Because actually, yes, that is true. That's how it computes. But it's hidden. I can't see it. Because what happens when I look at it? Every bit decides whether it's 0 or 1. The cat decides whether it's dead or alive. So here I look at that. And what do I get? I get the answer for a random value of the function. In this case, the qubits storing the X register were measured, and that wave function collapses, we called it. It turned into just, in this case, the value 8. And with that, the answer, so the function turns into the function value of 8, 16 in this case. What have we gained? Not much. We've just calculated the function for one value, for one random value. So yes, it did the calculation in superposition, we call it. We did it for all values at once, but it's not that easy, because when I look at a quantum bit, I only get one random value. So what do we have to do? We have to be a bit smart. In this case, we want to find the maximum. I can use something called the Grover's algorithm. I have all these values, but now when I look at it, I just get a random value. But we can change that. I can say I want to amplify the amplitude of the wave where the function is the highest. So that would be here, where if I knew it, it would be at 5. The near 37, that's where I want the wave to be stronger. The rest I want it to go down. So I want all the values to vanish. I want the wave to become very low and only be peaked around the 5, so that when I then look, then that's the value I get. So here, the Grover's algorithm allows me to calculate the function many times, and each time I can dampen the amplitude of the wave at the values I don't want. I can increase it at the values I want. If I repeat that enough times, the most fade out, and what remains is what I want, in this case 5 and the value near 37. So I need some way to then manipulate this wave to get the answer I want. And that is the art in writing quantum algorithms. Using the wave nature of my qubits to then get an answer I'd like to have. And so there's a lot we can do with Grover's algorithm. But there's one more thing we need to know to make it real. I need to understand, what do I need in a quantum problem? What do I need for quantum algorithm to be able to solve a problem better or faster or cheaper than classically? For that, I need one ingredient that the quantum computer has quantum speed up. That means that it can actually solve a problem with a better scaling than classical. When it increases the problem size, for example, for finding an optimum of a function or solving a problem, then the time to solve it increases as I increase the problem size. And quantum speedup means that on the quantum computer, here the dark line that goes up, it increases more slowly than on the classical computer, the blue line that just shoots up. So what we see here is when the problem is large enough, the quantum computer wins. But we also know that a quantum bit or a quantum computer in general is much more complex than a classical computer. Manipulating a quantum bit needs the right pulses being sent, and it's much more complex than just switching a transistor. And thus, a quantum operation will be slower than a classical one. But fortunately, due to quantum speedup, I only need to do fewer. How it means that for a small problem size, the classical computer will win because the operations are fast. They do just a few and they're faster. For the large problem, the quantum computer will always win because the scaling is better. What I now need is, I need to find out where's the crossover point. Where's the crossover point where the quantum computer becomes better than the classical one? And when we started looking at that for the first problems back in 2011, 2012, then I got the feeling, hey, I've read about that somewhere. I read somewhere about a machine that could calculate the number 42 in 7.5 million years. And it started looking like that because most of these crossover times were long, millions of years, billions of years. And for some problems, it was short. Then we tried to find out what is needed for that. Because to be practical, to be real, that crossover time cannot be more than a few days or weeks. I can't wait for a month for one number. It has to, because there might just be load shedding happening and it stops, right? So it has to finish in some hours or days. Also because I don't just want one number, I want to run something many times. So we need to find problems where the crossover time is less than a few weeks. Now, that poses a problem though. It's fine to prove theorems about the scaling. One scaling is better than the others. But to find out what is the crossover times, I need more than scaling. I need constants. I need to know exactly how fast is a quantum operation, how fast is a classical one. And that's where I need to speculate. So let me try to find some guidance that will help us find where a quantum computer will be useful for sure, and to find problems where maybe it will not be that useful. So for that guidance, I have to make assumptions. And on the left side here, I'm making an assumption for the classical computer. For the classical computer, I want to be totally pessimistic because I'm a quantum optimist, right? I'm building quantum computers. So I want to be pessimistic on the classical side. That is, say, the only thing I allow as my classical computation is one single NVIDIA GPU. Okay, I take the latest one, but only one. You know, data center, we have tens of thousands, but okay, I take only one. And on the quantum side, now here I'm optimistic. Here I put down the dream machine that I think I can actually design and build in the next decade. There's a machine with 10,000 error-corrected, reliable logical qubits with a logical cycle time of 10 microseconds. It runs at 100 kilohertz. That's fast for a quantum computer. And now compare what these machines can do. And in the bottom row here, you see just the I/O bandwidth. How much data can I load? We know classical computing and GPUs are I/O limited. I'm limited in loading data. I have big data problems, right? Big data is a problem because loading data is hard. And this machine can only load 38 gigabit that can only load 38,000 billion bits per second. It's very limited. That's why we have big data problems, because they want to load petabytes. Now, when I look at the quantum computer, if my cycle time is 10 microseconds, meaning I operate 100 kilohertz, I have 10,000 qubits, I can only do 1 billion operations per second. So I can never load more than 1 gigabit a second. This machine is 38,000 times slower in loading data. Ouch. If anybody tells you quantum computers will be good for big data because that wave function has exponential values in there, I said, yeah, okay, great, but I can't get it in. There's a bottleneck for loading data. So we learned from that immediately. Just being pessimistic classically or optimistic quantumly doesn't help us. Quantum computers will help us for small data problems and big compute problems. Seems obvious. This is a machine that computes fast. So we should use it for big compute problems. Now let's look at the computational power. The supercomputer I started on when I did my master's thesis was a bit less powerful than my smartwatch here. But at that time it was really fast. They operated 260 megaflop, 260 million floating point operations per second. The single GPU now does 2 petaflop, 2 times 10 to the 15 operations per second. I can't even imagine what number that is. But those are fast machines. The quantum computer, if you write down the best circuit for multiplication, optimize it, we estimate it can do about 10 kiloflop per second, 10,000 operations per second. And now we see, I told you, a classical computer is faster and cheaper than a quantum computer. A quantum operation is more complex than a classical one. Trying to make that quantitative, we realize 2 times 10 to the 15 versus 10 to the 4. It's 11 orders of magnitude different. Ouch. Okay, so that's, but I'm the quantum optimist, remember? Somebody could tell me, wait, my data center has 100,000 GPUs, okay, then it looks worse even. So let's embrace this 10 to the 11. That means not much. It simply means I need a problem where the quantum algorithm does 10 to the 11 fewer operations than the classical one. If the classical algorithm is so compute intensive, if it needs exponential time, if it needs 10 to 100 operations, and the quantum computer only a few thousand, then it wins. So we need to look at problems where there's enough quantum speed up to make that up. So these have to be problems that on the classical computer are exponentially costly and the quantum computer cheap, and small data problems. So with these guidelines, I can look at all the problems people told me where quantum will surely win, like big data problems or weather prediction, other things. And I find what really remains are the problems that are small data, that are exponential compute, classically, very little compute quantumly. And that turns out to be 2 classes of problems that we know so far. So one is cryptanalysis, breaking codes. I have a code, I want to break it. 2,000 bits is the input. Searching through all possible options to break it is hard exponentially. Shor's algorithm can do it classically. Okay, breaking crypto. Is that the application you want to build a machine for? No. With that, I can't make money. That just tells me we have to upgrade our crypto, make it better. The other application that we know for sure is chemistry, material science, clean water, new materials, better drugs, better solar cells, solving quantum problems in chemistry and material science. That's something where quantum computers have the exponential advantage. Now, why is that? And that's clear since Feynman back in the 80s said nature isn't classical, damn it. And if you want to simulate it, you better basically build a machine that works on the same principle as nature, build a quantum computer. So the idea of a quantum computer came from Feynman realizing simulating nature is hard unless we use hardware that works on the same way. That was the birth of the quantum computer. And that still is, we think, the main application. But then people on my team even told me, hey, Matthias, I'm disappointed now. I joined the quantum team because I want to change the world. And now you tell me the main application is chemistry. Who cares about chemistry? Well, there might be a few people in the audience here who care about it. But then to those people, I say, look, we call the ages of mankind by materials. We talk about the Stone Age and the Bronze Age and the Iron Age and the Steel Age and the Silicon Age. We define human progress through materials. And just imagine what we could do if we could design materials. Better batteries, I mentioned already. Better solar cell, new coolants, things. Or just imagine if you can build a computer that helps you design a chemical process to remove carbon from the air, to make clean water, to make fertilizer locally on the farm cheaply. That will change the life of people on the planet. And so then also I tell them 96% of all manufactured goods rely on chemistry and material science. And it impacts every person on the planet. So if there's one thing that you can do to have the impact globally, it is they are finding ways to do chemistry better. So with that, I'd say this is a worthwhile building. And when my boss asked me, why should we build it? Then I have to argue why it's a good investment for a company and whether one can recoup the money puts in. And the answer is yes. If we can really change chemistry, material science, manufacturing, everything totally, then there is big impact. And the way we do that is not just with quantum, but to use quantum and AI. I start out by simulating materials on classical computers. I use that to train the AI models. And I can use those models to faster simulate materials. You can basically train an AI to predict what the simulation would give me. I can use that to speed up calculations. We've done it once, showing that we looked to use that to define to find a new electrolyte for a battery. And in just 1 week, using AI, we could screen through 32.6 million potential material candidates to find one that looked promising, and we could make it, and it worked, and we made the battery, and we were working now on commercializing it. So with AI, I can do things faster. And they can start changing the way we do material science and chemistry. But we're limited by the limited accuracy of what I can calculate with classical computers. I started out by saying, look, a quantum bit is in 2 states, 0, 1, at the same time. When I have 10 quantum bits, it's 1,000 states, 20 million, 30 billion, and the same is true for the electrons in a molecule. So just as I said, when you have more than 250 quantum bits, number of states is more than the atoms in the visible universe. If you have more than 250 electrons, the number of states is much more than the pair of the atoms in the visible universe. So to simulate molecules and materials, we use approximations. They sometimes work, then we're lucky. They sometimes don't work, then we work hard on finding better methods. So the vision we have with the classical methods we use here is limited, it's blurry. Quantum computers will allow us to see sharp, to see the details, to really calculate the properties. And then the idea is we now use the results from the quantum computer to refine the models. We pre-train a model with classical data. We look for the cases where that breaks down. We then use the quantum computer to generate more accurate training data, and we use that to refine the model and get models that are better. And then we use those faster models and better models to solve problems and find new chemicals and materials. With that, I can then make predictions that are just right. They say, I want to find a new material for a battery. You find I want to find a better coolant. I want to make a new solar cell. I want to have safe replacement for a dangerous chemical. With the quantum trained AI models, that can become real. It not only gives me the candidate material or molecule, it gives me a way to make it, and it helps me assess the environmental impact. So in that way, when I have a way to really predict how nature works, then I can turn it around and use it to design chemicals and materials. Just think of ChatGPT and how we learned that it can write essays, it can draw pictures. With the quantum computer to train an AI, we can teach a quantum computer to understand chemistry and material science. And then just like now, we can write essays in text with generative AI. With quantum, we can get models that can design materials. I can just type in things like, please help me design a chemical process that removes carbon from the air and solves global warming. And it turns out, and then it says, hey, Matthias, why don't you try this? I just would love to be there. So, and we'll get there by a combination, as I said, of AI, HPC, and quantum. We need the HPC for the classical calculations, the pre-training. We need quantum for the refinement, and the core together will be AI. And we have quantum machines right now in our the cloud services. But the question is, what do we need to actually get there to train the models to solve the chemistry problems? The other point is that today's quantum bits are just too noisy. They're like spinning tops that fall over after a few thousand rotations. But my calculations will need to go for many hours, for billions of steps. So imagine you have 1,000 spinning tops that you need to keep spinning for many hours and days. That's hard. So that's the problem we have. That's when you call the That's why we say the current machines are noisy. And so we are in the era where that we call the NISQ era, the noisy intermediate scale quantum era. That uses the quantum bits as they are the noisy ones, we call them the physical qubits, to do the calculation. But where we need to get to solve the chemistry problem is about 1,000 qubits that live not just for milliseconds, but for days. And those qubits we call logical qubits. What we do here is we don't just take a single qubit, but we take many, hundreds of them. It's sketched in the middle here. And we redundantly encode the quantum state into many noisy qubits. Then we can find errors, detect them and correct them. So we need to get to 1,000 logical qubits that live for days. But the step in between we call level 2. That is where we start getting the first reliable logical qubits. And at the beginning of last year, there was no reliable logical qubits on the planet with which one could compute. And then our team looked at that and just tried out different ways of encoding the quantum information and found a way to make 4 logical qubits on the ion trap machine with continuum. So with that, we said we've entered level 2. We have the first logical qubits. And then progress was rapid. By September, we had 12. By November of last year, we showed on the neutral atom machine that we can have 24. And then we announced, and we are now selling machines to be delivered the next year with 50 logical qubits. So we're clearly in the next phase, level 2, where we have logical qubits and we can start doing calculations that one couldn't do before. And so we are selling machines now with 50 logical qubits, and will soon go to 100. And then I think in less than a decade, we may get to level 3,000 and more logical qubits fast for the chemistry problems that I'd like to solve. But let me also mention level 3. What's our plan there? What's our plan to getting there? Yes, one way is we can take the neutral atomic machine we have now and make it faster, much faster and bigger. But we also follow a second path, and we ourselves are building topological qubits. And we announced our first year QPU back in February. And we have from the start designed qubits and designed the quantum machine for scale. So let me tell you why we like the Majorana qubits and what is this special about them. This is a chip that right now contains 8 quantum bits. But in the same space, you can fit 1 million fast qubits. So 1 million fast qubits will fit in the palm of your hand. What we needed to get there was we needed to find the device or make one that contains a new phase of matter. like we have solids and liquids and gases of water. We can have electrical insulators and semiconductors and metals. The phase we need to look for is the topological superconductor. So for the topological qubit, we need the new phase, topological phase in a controlled way. And the type of material we need mirrors properties of a superconductor and a semiconductor in a way that doesn't exist directly in the material yet. Maybe with the quantum computer we can find one. What we do for now is we take a superconductor, put it on top of the semiconductor to make the composite material that has the right properties in a controlled way. And what is the magic that happens then? The magic that happens then is when you take two wires that you make in that way, you get four special topological modes at the end of these wires. And these are Majorana zero modes. They're essentially half an electron each in some way. When you take two of them and bring two of them together, those two can annihilate and be nothing, be gone. Or those two can combine and form one electron. That was first found in the 30s by Italian physicist Ettore Majorana. He wrote down a theory that had particles in it that could be their own antiparticles. They could either merge and vanish, or merge and be a new particle in two states. Unfortunately, Majorana boarded a ship to Sicily and vanished from Earth, and since then nobody found him nor those particles until we made a device that has these properties. So you can take here a quantum dot that's just a small quantum system. I can couple that to the two ends and I can measure the state. And depending on the total charge in the system, where it is, it can be an odd state that we call then the one state, or an even state. So these two combines can either form a 0 or a 1. And that way I've now made a device where the underlying phase of matter has the two states of a quantum bit. But the magic of this is more than just that I've made a new phase of matter with which I can make a qubit. With that, one could say, yeah, you've made the most complex qubit in the world, and it took us 20 years to make it. Now, let me tell you the secret. The secret is that on this qubit I've just shown you, with these wires, with the topological phase, with the Majorana particles, with that I can do all the operations that are necessary to make logical qubits just by measurements. When I have these two, that I couple, then I measure the qubit. I can do operations just by measuring other pairs, the vertical ones or this one and the neighboring ones. They can do all the important operations for fault tolerance for logical qubits just by measurements. And measurements are easy. Measurement can just turn on, and the measurement can be turned off. To start the measuring, I need to couple this quantum dot to it. So I open the transistor. When I'm done with the measurements, I close the transistor. How do I control the transistor? I control it simply by a digital voltage pulse. So the advantage of these quantum bits is I can just send in a standard digital voltage pulse that comes from a transistor. No fine-tuning needed in the amplitude, no fine-tuning needed in the timing, because the measure for microsecond or two, I don't care. I want this Schrödinger cat to become dead or alive. If I look longer, it just stays there better. While most other quantum bits need a finely tuned analog control signal where the timing and the amplitudes have to be just right. With the topological qubits, I can simply use a transistor. That means I may have produced the most complex quantum bit ever, but when I want to scale it up, it becomes easy because I only need transistors to control it. So that's our plan for the future. But imagine now in the next 5 years or so, we get to a machine that can solve problems I can't do classically. Interesting ones, hard ones. Then I want to enable the beneficial applications globally while mitigating the risks. And then people tell you, no, we cannot export quantum computers. We can't give people access to it because, as I mentioned at the start, quantum computers will also be able to break crypto. But my answer then is, to protect from that, what we need is we need to upgrade our crypto. The current public key cryptography with the RSA ECC will be broken by quantum computers with about 1 million quantum bits. The symmetric key crypto is safe. Some people tell you it's not safe because you can use Grover's algorithm. But then you can reply, Grover's algorithm only has near quadratic speed up. It's not the exponential one. I need to beat that big factor ahead. So those are safe. Because the clock speed of quantum computers are safe, symmetric key cryptography is safe. Public key cryptography's impact is, so what we have to do when we build quantum computers, we have to wherever near possible use symmetric keys and transition to new post-quantum some near public key cryptography as soon as possible. So to keep the world safe from quantum computers, we do not stop the export of them to South Africa, but we rather harden our crypto. We make our locks better. So with that, then we say the main application we see after that, after we've changed our locks, after we are all quantum safe, the main application is chemistry. And with that, there should be no problem, right? We can just sell that machine to anybody. However, as people in chemistry know well, chemistry is intrinsically dual use. Material science is dual use. The first the human in Africa who lifted a rock to kill an animal saw that the rock is dual use. It can be a weapon or a tool. And Alfred Nobel's story of dynamite is about the same. Kind of chemistry is intrinsically dual use. And so we have to then start thinking about kind of how do we make sure that we use that capability in a responsible way. And that brings me to the topic topic of responsible computing. And while there are colleagues who talk about responsible quantum computing and quantum ethics, I see the problem bigger. Because as I've shown you, we can already do new materials with HPC. We made it faster, for example, for the battery with AI. And quantum will just make it more accurate. But it's basically the same challenge. How do we use computing in chemistry, material science, be it AI, HPC, quantum in a way that's safe and responsible? We need to work out the frameworks for that. Then ultimately, I think it may have to come down to your customer process, like in banking, where I need to understand what does the user want to do with it. Because any chemical can be used for good and bad. The cancer drug ultimately is designed to kill cells. So that's one challenge we'll face. But facing those challenges, making our crypto safe and addressing the dual use issue, we still want to build the quantum computer. And the one limiting factor we have is talent. In order to make it real, we need the best people on the planet. No country by itself, no continent by itself will succeed. We need the global genius for that. And that's why we said that we need to find ways of getting more people engaged in quantum. And that I worked with the Foundation in Geneva, Chester, that also Francesco works with, to think about what can we do to bring more people to quantum. And then we decided we need to bring quantum training, access, education to the whole planet, especially to the global south. So we started the Open Quantum Institute in Geneva, and I want to end with the video about it. Thank you, and I want to end with a quote by Anatole France to accomplish great things, we must not only act, but also the dream, not only plan, but also believe. Thank you.
Thank you very much, Matthias, for a fascinating talk. I'm sure we have time for a few questions. Anyone like to ask Matthias something? Please. Microphone is coming.
Thank you very much for the interesting talk. I have a specific question about that. You mentioned quantum data for training AI.
Yeah.
Can you a little elaborate on that? Which modalities did you use? Quantinuum, atom computing, and how many qubits? I'm very curious.
Okay, so what I showed you is the vision I have for the future. That's how I think we will use the quantum computer, because of a few reasons. First of all, doing a quantum computation, even on a big scaled machine, will take hours or days, while the inference call to model takes milliseconds. Currently, classical calculations already take too long. That's why we replace them with an AI. The second is, if I train an AI model based on quantum data, I can just give that classical model to somebody, and they can just do it easily in milliseconds, get the answer. That's quantum accurate. Now, we have demonstrated training models from quantum data on current ion trap qubits. Used 4 logical qubits on Quantinuum to solve a problem with 2 electrons in 2 orbitals. We learned the wave function using AI, and we trained the model based on that. There's something that I could do on a whiteboard, I think, still, but we showed it can be done. And then we showed that we can really learn models better with better training data. We've shown that. But we don't yet have the quantum computers that let us do big chemistry problems that they cannot do classically. So currently what we use is we use classical GPUs to calculate the training data more accurately and train with it the models more accurately. In the future, we'll use quantum computers.
Thank you very much.
Hi, thanks. Great talk. I'm Bruce Bartlett from the Maths Department here. I actually work in topological, or the maths of topological quantum computing.
Yeah.
We've got a student in that as well. But just wondering about the Majorana thing. So first of all, I agree with you about your vision. It's very realistic to me. Like you saying, do quantum training for the classical computers. I like that. That sounds like a very realistic vision. But you know, there's a lot of controversy about your claim that you have made the Majorana topological quantum computer. Can you just comment on that? Because there's a lot of people who are very doubtful that you actually did it. Yeah.
We posted the paper recently that has the data that people asked for.
I think there's a question at the top.
So the proof ultimately is, building a quantum computer that can compute. Then any questions will stop.
Sorry, I'm a material chemist. I'm just interested in the actual material that you use in the Majorana qubit, the quantum dot itself.
That is heterostructure. The quantum well is indium arsenide, and there's a barrier, and on top aluminum as the superconductor. The detail is in the width of that and how you make it and so on. That's where the secret lies. And coming back to the other question, there was controversy about papers from Delft from 8 years ago that were withdrawn. Those were devices built from a transparent material with dimensions where when you near simulated, you see that in those devices there are no Majoranas. So the choice of material is really crucial here.
Any other questions or comments? Yeah, here, please.
Sorry, Prof. I'll like to know about your side of Microsoft. How open is the development to other? Is it a more of an open development where you have other companies working with you? Is it all in-house in Microsoft and all data is in the house?
Yes and no. It's quantum after all. Okay. So we are a platform company. We make Windows operating system for any classical computer. We build our quantum software stack, our quantum operating system for anybody's quantum bit. The NIG 50 logical qubit machine we build, we make with the NIG part, the company, the atom computing, and we make our own qubits as well. So we partner and build things in-house. So for the software stack, the applications, we partner, and for qubits, we partner. For the details of how we make our topological qubit, that's a trade secret. That's part of the near controversy, because we'll say, be open about this. We know there are things that are trade secrets. We'll share the data, but not how we made it. But for most parts of the stack, we're totally open. Thank you.
Thank you. Another edition of that. Yes.
Thank you.
It was off. Sorry. So thank you very much.
Thank you.
Thank you very much.
Thank you so
Something to
much.
read on the plane on the way back home.
Thank you. I will. Thank you.
Thank you.
Thank you.
According to plan, there should be some snacks and drinks waiting for us outside. And I would like also to thank all the online participants. Yeah, thank you very much.
Thank you.